Hello everyone, my name is Catherine Elwell and this is my poster, Glow Power Project Converting Bioluminescent Light for Solar Panel Use. To begin, the ocean is not well explored. Certain areas such as cave systems are less likely to be explored by means of satellite photography or ship-pulled sonar. ROVs and AUVs are controlled vehicles that can easily explore these areas due to their small size. However, current technology is limited due to long-term power demands without intervention or additional equipment. Glowworm caves, such as New Zealand's Waitomo Caves, host a large assortment of bright bioluminescent life. This study aims to use the projected natural light from these creatures to sustainably power a photovoltaic panel. Common photovoltaic or solar panels are available in a variety of shapes and sizes. For this study, a filter solution will be researched to fit across a basic blue silicon 4x4 inch panel to convert the bioluminescent light for the solar panel to generate electricity. The power generated can be used to supplement scientific instruments in caves and other dark locations. The Waitomo Caves are used as proof of viability due to their renowned bioluminescence. Comparisons will also be drawn with other bioluminescing species to analyze the difference between the filters and whether this system can be taken to other cave environments. The main investigation will analyze a few select Waitomo species and others from North America and Africa for adaptivity. The wavelengths of the found species will be averaged to the peak conversion rate of the filters for selection. Price for coverage will also be factored in for the best filter selected. These are a few of the bioluminescent species investigated. The Waitomo species shown are Arachnocampa luminosa and Arachnocampa flava. The North American species are Orfelia fultoni and Arachnocampa Neoditomyia. A South American species, Neoceroplatus betaryiensis, is cousin to Waitomo's luminosa scusae. With the control surface the blue common panel, the selection of filter solutions were identified from a wide range of accessible products as an overview of the best each category can offer. The tested filters are an Astronomy High Point No. 58A green filter, Casandora Yellow Shade paint, blue light glasses filter, Fluorescein fluorescent medical tracer powder, and Alexa 488 biomedical fluorescent dye. These are the results of the emitted creature wavelengths and the filter peak conversion wavelength from the bioluminescent to panel utilized light. The creature average wavelength was 460 nanometers, while the two closest were Fluorescein and Alexa 488 at 493 and 507 nanometers respectively. Figure 3 shows the price to cover a common panel with the respective filter solution. The two cheapest options were Fluorescein and Casandora Shade at $6 and $7 respectively. Bringing into account the closest in converted wavelength, the most successful filter option is the Fluorescein. As previously tested, Fluorescein was successfully put onto a panel for robotic usage. Fluorescein is a medically safe dye and is inert once applied to other objects. It is not researched whether fluorescein will instigate biofouling. Even so, fluorescein has been tested and is safe for electronic use. Extended research will be required for implementation of this filter for every situation. However, due to successful land testing, fluorescein is the superior choice. Fluorescein is deemed an essential medicine by the World Health Organization and is safe for most instances of organic interaction. The goal of this material was to be easily accessible, adaptable for vehicular shapes, and to be inexpensive as an adaptation for existing hardware. Fluorescein is a perfect candidate for these requirements. With this utilization, more of the ocean's unexplored or dangerous areas can sustainably be powered by discovery vehicles. These are all of my sources for this project, and thank you for listening.